next session is about multi-core in VPP. I will try to explain how the VPP works in case when we are using multiple CPU cores for packet forwarding. Let me start with explaining first what are the modes of operation we have in VPP. So we have the single thread mode, which is what you saw this morning, which is basically just a main thread doing all the work. Then we have multi-thread work with worker threads only. This is basically a split where you have the main core doing the control stuff, like CLI handling and updating the data structures and so on. And then having the worker threads, which are basically doing packet processing. Third one is multi-thread with IO and worker threads. This is one a bit specific case where we are basically using one thread to receive packets. And I would say the IO is maybe a wrong term to use because we are actually just doing input on such threads. So idea is that one thread is receiving all the packets from the interface, doing software hashing, deciding how to spread the traffic to the different worker threads, and then using the hand of dispatch mechanism to basically send frames to the different worker threads in VPP. And last one is basically very similar to the previous one. The difference is that in this case, we are basically using the main thread to receive packets and then to hand over those packets to the different worker thread. Just to make one statement here. So this is how it works today in VPP, and we are actually planning to do some rework of this stuff. So idea is really to reduce the number of modes to really two, single thread and multi-thread. And what we want to do is basically to create the graph node, which will be a universal graph node, which will be in use for doing the hand of dispatch of packets between the cores. So basically replacing the case number 3 and case number 4 with the universal graph node, and you have only worker threads, so not having the special IO threads in VPP. The reason why we want to do this is basically to reduce the number of different packet paths in the DPDK driver code, because right now we actually have 3 different input paths inside the DPDK code. We have the standard DPDK input node, then we have something called DPDK IO input, which is basically mapping to the case number 3. And then we have the case number 4, and then we have something called DPDK thread, which is mapping to case number 3. So basically, we have 3 different code paths for receiving packets in VPP today, and we would like to reduce this to only one. And idea is really to just have a worker threads, and then if you have a need to dispatch specific frame of packets or packets coming from the specific interface to different worker threads, you can basically have a universal graph node which is going to do the same functionality. So how it looks today. If you want to do a multi-thread configuration in VPP, you need to specify this in the startup config. And we have a section inside the startup conf which is called CPU. And there are basically 2 ways to do that. First one is to use automated placement. A second one is to do manual placement. So if you are doing auto placement, you are basically saying skip one core. Typically, we want to skip core 0 on CPU because it's used by different stuff and operating systems. So we are typically skipping one core. And then we want to have 3 worker threads. And VPP will basically discover the available threads on the system, and it will try to use first 3 available threads which are in the system. If you want to be more specific, and if you want to really map the different stuff to the specific cores, you can use manual placement, where you are basically saying main core should be on L core 1. We want to have 2 IO threads, and they should be on thread 3 and 19. And then we want to have 4 worker threads, which are 4, 5, 20, and 21. So basically, this is the full flexible way you can really say exactly what you want to run on which CPU core. Auto placement is if you are really not, if you have the system only for VPP and you just say, give me a 5 workers, and I am using everything for VPP. If in case where you want to really to map different cores to different stuff running on the server, you will probably use the manual placement to fine tune the stuff and to basically assign where is running, what is running where. Okay. So basically the commands which are related to the CPU placement are on the left side. Core list, there is also, instead of core list, you can use core mask, and that is actually equal to dpdk core mask. But it's more human readable if you are using core list. It's basically, you can say 1, 2, 3, not calculate the hex mask of cores which you want to use. But you can also use core mask IO instead of core list IO. And yeah, so this is the specific one for this last case, multi-thread with main thread doing IO. So for that command, if you say main core IO, you're basically saying that IO thread should be executed on the main core. But as I said, this is something which will probably change soon. So I would just focus on the first 2 cases, single thread and multi-thread with worker threads only. Okay, so when you run VPP, if you want to check what is actually happening, you can do command show threads, and then you will basically see the exact setup which is currently running. And here we have the main thread running on the L core 2, which is basically second core on socket 0. Then you have the 4 worker threads, which are running on 2 on socket 0 and 2 on socket 1. And finally, you have 2 IO threads which are running on the socket 1. You can see the state, and you can see even the Linux process ID for every single thread. So if you're doing some performance measurement, you want to run perf top on the worker thread, you can just use the process ID of the specific worker thread and monitor it with perf top. If you're using the IO code today, it's basically a dpdk input node which is slightly modified in the way that it will not dispatch the frame to the next node, but it will try to hand off the frame to the different worker thread. So actually the dpdk input node, which is called actually dpdk IO input, is doing standard dpdk receive stuff, which is the normal node doing, but also it will calculate the hash, and it will calculate which worker thread should receive this specific packet. And then it will basically send this, it will hand off this frame of packets to the worker thread, and on the different worker thread you will get that frame of packets, and then it will start flowing through the standard path through the dpdk graph tree. So basically it's only about input node. How basically you have input node on the different core than all other nodes in the VPP. Yeah, so because mainly what we are using on and for all benchmark testing we are using RSS, and I will come back to this later when I will talk a bit about receive side. So basically 3 and 4 are basically software RSS, where when you have one queue coming from the interface and you want to spread the packets coming on one queue from the interface to different workers. And you want to do this either because you don't have a hardware RSS, or if you have very specific requirements, like we want to do, I don't know, layer 4 lookup into the packet before deciding where to send the packet. Yep. So there are some cases where this can be used. We are not using this frequently, and that is actually the problem, because we are not using this frequently because we are mainly using RSS. So code path 1 and 2 are actually the same one, and it's well maintained. It's stable. Code path 3 and 4 are not very frequently used, and they're out of sync. And that is actually my motivation why I would like to completely get rid of them and basically try to make it in the way that there is just one code path on the receive side, and then to have a very small graph node which is just taking care for handing off packets between the threads. Okay, so thread synchronization. So actually initialization. If you take a look into the source code, you will basically see that we are using a lot of macros, and we have something which is called vlib register thread, and this is basically macro which is registering the new thread. And whatever you actually use in the macro as a short name, it will be used in the startup config. So you remember that we have command worklist-workers and worklist-io. This is basically this name. So it's very easy to create new type of threads in VPP. You basically just register put the new registration macro. You say what is the name, it's workers. There's a short name which is used in some outputs. And you say what is the main function for the thread. And heap size. And based on this, and based on this registration, VPP will give you all the stuff related to the core assignment and all the stuff I showed on the previous slide with startup config is automatically given to you. So if you say, I don't know, QoS, worker thread, or QoS thread, you can just say name equals QoS, and then in the startup config you can just say core list-QoS and specify which cores will be used for running that specific thread. Okay, so this is another very important thing, how VPP works in threading. So basically, when we need to update some data structure, typically data structures are updated by the main thread. And if the specific code is not thread safe, then we need to stop all the worker threads. And we have this, what is called thread synchronization. We have basically 3 functions, which you will find in some places. And that's basically sync, release, and check. In other words, if the main thread wants to update the data structure, it will basically called barrier check. Check will basically try to stop all the worker threads. It will stop them. You will update what you need to update. And then with release, you will basically release worker threads and they will continue working. Also, if we are cloning the data structures, so that's basically, it's very, very complex functions in vlib threads.c, which is doing that stuff. We are basically, many data structures we are basically replicating and copying to the different worker threads. So basic idea is that if you want to do anything which is updating the data structures which are used by the worker threads, and you are not thread safe, you just stop them, update, and release them. And typical example is CLI. So this is a macro we are using to register the CLI command, vlib CLI command. So basically we are saying CLI command IP route. This is the help, which you are going to see if you do the help for the CLI. This is the function which is doing the CLI work, and then we have this. So basically we are assuming that code is not thread safe but by default. So if your CLI is really not touching anything and maybe just showing some data and not doing anything, you can say this is MP safe, and then CLI subsystem will not stop worker threads when you're executing the CLI. So this is basically how the threading synchronization works. It's very simple, very basic. It's basically stop all the threads, update the data structures, start them. So this is a worker thread main dispatch loop, which is basically the main function which is registered as a thread. And you can see that we have infinite loop, and first one is barrier check. So if we say that we want workers to stop, this guy will just start waiting, looping. And we are done, this guy will continue, and then we will have frame, vlib frame, QDQ internal, and all the stuff here, which are basically handling the graph nodes. So you see this one. This is a dispatch node function, which is basically okay, so this dispatch node is actually the guy which is calling the input nodes, first one. You see vlib node type input. So basically this guy is calling the input nodes because the input nodes are polling. And then this guy is calling pending node. Pending node is node which have something to do. So there's some packets where, or some vectors or packets waiting for the specific node. So this is really the main dispatch loop for the worker thread in this file.
Hi, Daniel. It's not a question on how it works, but how often it is used and how it impacts traffic. If we assume that we update the fib, for example, does this mechanism is this mechanism used or not?
No, fib is thread safe.
Okay, so there.
Yep.
This is used for very little portions of the code.
Yes, yes.
So, but for the main data
idea is that you try to do it thread safe. And if your code, and the reason why we have it this way is that we actually implemented threading quite late. So originally VPP was single core application. So instead of really reviewing the whole code base, we basically made an assumption that everything is not thread safe unless you say different. But then we did some work on the important parts of the code, like fib, and we made the fib thread safe. So for example, fib will not stop workers. But some CLIs will, unless you really say is thread MP safe equals 1.
So the question is, for operations, if you have something running and you have a problem, so you have to access the CLI to do things. The question is how secure I am to use the CLI where there is a pending problem, and I don't create even more problems by introducing some kind of.
Well, typically the CLI is not really CPU intensive. So typically, yeah.
So
I mean, it will stop traffic, but that is really, really very, very small fragment of time. So if you try to run the traffic full rate, completely maximum rate you can do, and try to use CLI, you will possibly observe few packets of it, but it's not really that you will have a significant impact. Okay, so next thing which is important is to understand how VPP is distributing packet load between the cores. And that is what we already discussed a bit before. So mainly we are using the RSS engine on the NIC. We are basically saying to RSS engine on the NIC that we want to use 2, 3, 4, 5, 6, whatever the number of receive queues, and that we want to use the specific RSS mechanism which is available by the NIC. And what we are going to get, we will basically have the few queues which are handled by the DPDK driver, and we will try to basically pull those queues from different worker threads. So if you take a look into the code, this is an important function because it's doing that work. We are basically looping through the list of devices by CPU, and based on CPU index. So this code will be executed on all worker threads, but this line here will actually give us the number of thread where we are running. So if we are running on worker number 1, CPU index will be 1. If we are running on worker number 2, CPU index will be 2, and so on. So this is the way how we can know that our functions is running on the specific worker thread. Then we are maintaining array of vectors of devices, and actually maybe this session should be after the infra section, which explains what the vectors are in VPP. But basically, vectors are resizable arrays, which we are using very, very frequently in VPP. And a resizable array of anything. So it can be a really resizable array of anything. And what we have in DPDK driver is basically this one, DPDK device and queue structure. It's a very simple structure, which is described here. It's basically device ID and queue ID. So if we have 4 worker threads, this CPU index can be 1, 2, 3, or 4. So basically, it's array of 4 vectors. And every vector is basically array of these structures, which basically contains the DPDK device ID, and it contains DPDK queue ID. So if you're not running RSS, QID will always be 0, because then you have just one receive queue. If you're using RSS, QID can be 0, 1, 2, 3. In other words, by modifying this vector of array of vectors, which size is equal to the number of the worker threads, you're basically saying which worker thread which will pick which input device and which queue. And even better, you can really update this in runtime. So if you want to move specific interface and a queue on that interface to the different worker thread, you can do that. And if you're not changing the NUMA node, you can even do that without losing every single packet, because it's completely dynamic. You can just change move the specific instance of this structure from the CPU 1 to CPU 2, and immediately this function will basically start polling that specific interface and specific queue on the different worker threads. Okay, inside the DPDK driver, we have one structure which is called DPDK device T. It's a basically structure per interface structure, and this per interface structure is actually the one which is just a second. Yeah, so basically the per interface structure contains all the data we need to know about the specific DPDK interface. So this loop is basically going through the list of interfaces and queues which we need to process on the specific worker thread, and when we find such interface, we will basically just call the function which is doing the real work on the receive side. So with this way, we are basically having the ability to really process different interfaces and different queues on different worker threads. And you can change this dynamically during the runtime. Okay, we have a CLI for this. So if you do show DPDK interface placement, you will actually see what is the current state. So thread 1, worker thread 0, which is running on the logical core 5, is handling 10 gig 200 Q0 and 10 gig 201 Q0. And then we have another thread 2, which is second worker thread, running on the physical on the logical core 6, doing the 10 gig 200 Q1 and 10 gig 201 Q1. So this is the current state. And if you want to change this is a sample command: set DPDK interface placement, interface name, queue, thread. And after executing this command, you will see that actually this guy, he was before on worker 1, and now he is on worker 0. Well, first one, yeah, the first question is, should you really poll in that situation? Are you really going to poll 100 containers all the time? Or maybe in that case, it will be better to do kind of interrupt kind of notifications instead of polling. And regarding distribution, yeah, I mean, that should be some logic which is on the higher level. We have mechanism to change. So what we have, the native drivers are more or less all interrupt driven. So netmap, AF packet, and tantap. And actually, the netmap is much faster than AF packet. Okay, so we have another problem which needs to be solved here, and that is how to handle the transmit side. And yeah, there are some NICs which have a lot of transmit queues, and in that case, it's quite easy. If you have 4 worker threads, you just request from DPDK to give you 4 queues, TX queues. You map one TX queue to the one worker thread, and you don't need any kind of locking. The DPDK guy will just use his own queue for every worker will have own queue to transmit packets, so problem is solved. But this is not always the case. You can have NIC which don't have enough transmit queues, and even the powerful NICs today have some issues. So, for example, we had a situation with Intel Fortwheel. We are doing large-scale testing with I think it was 9 Fortwheels, and every Fortwheel having the four for RSS. I mean, it was like 72 worker threads in total on VPP. And we actually hit the limitation on the fourth wheel, which is 64 transmit queues. And yes, this is not what is written in datasheet, because datasheet says much more. But the problem is that you cannot allocate queue number 64. It just fails. So then the question was really, do we really want to have so much queues on the transmit side? And can we just try to reduce this in some way that we are still effective? And also to fix the problem when we don't have really the big number of queues. So we are basically doing very simple locking on the transmit side. And this is actually the lock function. So first line, this guy is actually telling us if it's a pointer. It's a pointer to one single cache line. And if we need to do locking on the transmit side, so this is per interface information. If you have multiple interfaces in VPP and few of them can have enough queues, those interfaces will have null in this pointer. If we want to do locking, or we need to do locking, then this guy will basically be pointer to the memory, 64 bytes of memory, where we are using as a lock. And 64 bytes is because we want whole cache line to be for us. We don't want somebody else to share that memory. So we are allocating basically for all NICs where we need to do a locking on the transmit side, we are allocating that 64 bytes of memory. It's basically unused except 1 byte, and that byte can be 0 or 1, locked or not locked. And then when the TX function comes to this piece of code, it will basically do atomic lock and test for the specific queue, and it will basically spin lock up to the point when the interface is released. And this is actually what was initial code with single lock. But actually later we realized that if we have like NIC which supports 4 TX queues and we need 8, it's stupid to limit us to 1 TX queue. Why we cannot use 4 of them? And this is actually this math which we are doing here. If we hit inside this loop, if we found that there is a lock on the queue number 1, we will try queue number 2. If there is a lock on queue number 2, we will try number 3. And when we are spin locking, we are not locking on the same one. We are really locking on all available queues until we find one which is available for us. And then we will set it to 1, and we will start doing the work. And the end of this critical part of the function, when we are done with the queue, we'll remove lock from that specific queue. So basically, after this one, we have code which is doing DPDK RT TX burst of packets to the DPDK. And when we are done, we are removing lock. And yeah, this is basically setting back the lock to 0. This is when we are done with the queue. And my last slide on this topic is something which you need to be aware when you are doing writing the graph node function. And if you want to run that as a multi-thread application, never use the same structure on all worker threads on the same time. Very simple case. You have one counter inside your graph node, which is just counting something. And if you have 2 worker threads updating this counter, you will see a serious impact on performance. Because your threads are running on the different cores, you have the different cache hierarchy. Every time when you try to write to this one, you basically need to do the cache synchronization between the 2 threads. CPU needs to send the whole cache line to the different thread, and so on. So basically, writing to the same place on the same time from 2 different worker threads is a really bad idea. So what we are doing typically, first we are trying to align data structures to be aligned with the cache line. So basically telling compiler that this structure in the memory should be aligned to the cache line, which is typically 64 bytes, but there are some systems which have a different, like ARM ThunderX, which is 128. Then this line will not just align this structure to the cache line. It will also make this structure big, one cache line, one or more cache lines. So basically, even if you have one U64 value in this structure, the size of this one after applying this macro will be 64. So if you are building an array or vector of those structures, each of them will fall to his own cache line. And then every worker thread can use his own instance in the vector. So let's say that this is allocation. Here we are basically trying to get information about this thread main is basically structure. We have information about number of worker threads. So there is a macro which is called vec validate align. Vec validate align is basically creating the ensuring that the vector is sized at least this amount of the second argument is number of elements. So we are basically creating the vector of structures, which is equal to the number of threads which we are running on the system. Basically, replicating this structure, if you have 4 worker threads, you're basically creating an array of four instances of this structure in the memory, which is every instance is aligned with the cache line and sized with the cache line, basically ensuring that the second one in the array will be in the different cache line. With this approach, when every worker thread is writing to this counter, it will not affect another one. And then finally, inside your code, inside the graph node, the same trick we used before. We are using get CPU number to get what is our CPU number for this specific thread. And then we are using these counters to basically increase this value. So this is really maybe the most important thing you need to be aware, because all the stuff which you are doing inside the graph node in VPP doesn't care much if you are running multi-thread or not. But this is important because it will work perfectly fine when you are running a single core. When you start to do multi-core, you will just see serious impact on performance, and you will not scale linearly in that case.
So if someone wants to read this counter that now has a per thread instance, is that up to the application to accumulate?
Yes.
There is no built-in support for...
No. I mean, we have counter support, and the VPP, I use counter as a sample here. We actually have the functions which are taking care for this, for the standard node counters. But always you have something which is specific for you. And if you want to sum, you just need to sum this value at the end. So if you have a CLI which will basically display this counter, which is sum for all threads, you just do vec for each, and then go through them, sum them, and display the sum of all of them. But the important thing is that the worker threads are really having their own data structures. So as you already noticed, there is a directory called build root. This is a place where we are actually building the VPP. And you can see that we have something called build VPP debug. We have something called build VPP native. So this is basically a place where we are building the debug image. This is a place where we are building a release image. Then we have install, which is also equivalent, place where we are installing the built packages. And we have the same for VPP. So we have VPP debug and VPP. So what is here is actually what is called a tag. So you can have platform, and platform can have different tags. You can have tag which is a debug tag, and you can have the release tag. So definition of packages is inside build data, and there is a directory called platforms. So this is basically the place where we are defining the different platform. And I mentioned yesterday we have something called VPP as a platform, which is main one we are using, but then we have something called VPP Lite. We have platforms which are optimized for or built for specific different microarchitectures like MIPS or ThunderX or something. And in this file, we are basically saying what are the... So the VPP build system is actually using the packages, and every package is using auto tools to basically create the set of make files. It's it's basically, as I mentioned yesterday, it's a legacy. It's the way how we are building the legacy images in the past. So basically having the different packages, and actually this build system is perfectly fine to build the tool chain. So if you can even have your own version of GCC and libc and everything built as part of the build process. What we have here is really the light version of that, because we removed the toolchain support. We are now relying on the standard toolchain, which is part of the operating system. But really, if you want to have your own toolchain, your own compiler, you can do everything with this build system. That's why it is built in the way like it is built. You can see that this is basically a file which defines the platform. And inside the platform, you can define the root packages. And we have a package which is called VPP. We have VLib, VLib API, VNet, SVM, which is the shared memory stuff, VPP API test, which is a command line tool which we are using for testing the APIs, and VPP API, and which is I think bindings for different languages, and Gmod is Ganglia, I think, so support. Then inside this file, we are basically defining the standard compiler stuff. So platform name is VPP, but then we have a tag, and that tag can be either VPP or VPP debug. So you see VPP debug definition and VPP definitions for C flags and LD flags. That basically means that we are passing different command line arguments, and if we are building the debug build, we will pass optimization to 0, we will set clib debugger macro, and so on. If we are building for a release build, we will use O2, and we will not set the clib debugger. And basically, unsetting clib debug will do a huge change in the code, because it will remove all the asserts and all the other debugging stuff inside the code. So this is basically why we have the debug and release build. This is the place where this stuff is defined. And then there is some stuff here which is commented out, but you can use if you have a special reasons for doing so. Like if you want to link with the external DPDK, for example. So today what we are doing, we are basically fetching the DPDK tarball. We are untarring the tarball. We are applying our own patches. And then we are building our own copy of DPDK. And that is all part of this process. So basically build tool is doing this. And that's why when you download cloning the VPP repo first time you do build, you will actually see that it's downloading the DPDK tarball from the internet. But if you want to have your custom DPDK version, you don't want VPP to build one, to link instead to the external one, you can basically uncomment those lines and set them. So there's even support for the shared DPDK, or it can be static. And so you have basic options to use either internal version of or external version of DPDK. Also, this is something which is quite recently added. This is what we are building for. So this is the optimization of the code, of the release code. So we are tuning right now for GCC flag, which is Core i7, and that is basically Nehalem architecture. But we are saying also that we would like to have it tuned for the Sandy bridge. So basically using the instruction set which is available in Nehalem, but optimized for Sandy bridge. And we are doing the same for DPDK, basically saying that DPDK should also be built with basically SSE 4.2 support. Then we have the similar file, which is called this French keyboard is killing me. We have another platform which is called VPP Lite, and file is actually quite similar. There is no DPDK here, so there is no DPDK on the list of the packages. But again, we have definition for Lite, for release build, and for debug build. And you can notice that here we have always the name of the platform. So in the previous file we had VPP, here we have VPP_Lite. So basically, this file is telling the build system what it needs to build and what are the dependencies. Then you have for every single package, you have the basically file which is defining how to build the specific package. So if you take a look into the build data packages and then VPP infra, this is a very simple one. This is the infrastructure library which doesn't have any dependencies, so it's very simple. It's almost empty file. But then if you look into for example, VLab, it's a bit more. So basically, we are saying that VLib depends on VPP infra. So basically, with this line, we are saying before start building VLib, you should build VPP infra. And then we have special treatment depending on if we are using DPDK or not. So platform VPP Lite will say VPP Lite uses DPDK equals to no, and then we will not do stuff which is inside this if not equal block. Then with the special case is DPDK, and I will show you how it works. It's basically in the DPDK directory. There is you can see that we have one makefile. This makefile is responsible for building DPDK. And then we have directories for every DPDK version we are supporting. So we have starting the DPDK 2.1, 2.2, and then we have the 16.04. And DKMS directory is basically just the stuff needed to build the DKMS packaging for Ubuntu. And if we go into the makefile, this makefile is actually I will show you the important part. This one. So what we are doing, we are basically customizing the DPDK configuration, which is default one in DPDK. The reason is that there are some stuff which we don't need, so we don't want to spend time on building the components which are not needed. Then we are enabling some debugs if you are using the debug version of VPP, and so on. So basically, there is a makefile macro which is creating. So basically, we are first using CPP preprocessor to take the defaults from DPDK. That is the second line, and then we are using this macro to basically update our custom config. And this is more or less what we are changing. So for example, we don't need stuff which is here. So we are setting no for all of them. Distributor, power, ACL, LPM, timer, and so on. So all this stuff is basically disabled. Bond interface, which is I think by default disabled, we are enabling because we have support for bonding, and so on. So basically this is how we are creating the custom DPDK config, and then when we create the config, then we start building the DPDK. Useful trick here is that you can to avoid downloading DPDK all the time. There is actually a place where this makefile will take a look for DPDK tarball before it starts downloading. So even if you wipe out your Git or if you make another clone, it's a good idea to basically put the DPDK tarball to your home directory into downloads, because this makefile will just check if the file is there. If file is there, it will use that file instead of downloading one from the internet. And for every tarball, we have checksums. So when we are downloading, we are checking checksums. So if there is some issue with downloading, the build will stop. We are actually checking checksums on every build. So even if your file is corrupted in the download directory, the build will fail because of that. Yes, we have a support of CLang also, so we can build VPP with CLang without issues. Yes.
Are you testing with ICC?
Yes, I mean, I make it working at some point, but I'm not testing it frequently. So it works, and actually this makefile is even not updated for ICC. Oh, maybe, I'm not sure actually. I think it's not. So VPP is building without issues. At least it was building last time when I tried to build it with ICC.
Do you think ICC could bring some benefits to VPP?
I don't know. What do you think?
We should ask the question.
Yeah, maybe.
We should try and see what happens.
Yeah. We can ask Maciek to test. I have idea. Intel needs to provide you a license, and you test with ICC.
I can do that. I can provide the license.
Very good. Yeah. Okay. So if you take a look into the standard package, so basically every directory in the top level directory is basically a package for the build system. So we have something called vlib. We have directory vlib, and if you go to vlib, there is actually makefile.am, and if you need to add the new C file or H file to build to the specific package, you just update it's a standard auto build file. So it's automake.am and configure.ac. It's not very advanced. It's really a basic auto tools setup. And for your typical use, I would say especially when you're starting, I think the makefile in the top level directory is the most convenient one. That's why we put it there, because you really just do make run, make build, and it will take care for everything. So if you type if you just type make in the top level directory, you can actually get a help. There's even C tags and C scope stuff here, Doxygen. Packaging is here, so more or less whatever you need to do with the build system is here, unless you are creating a new platform or doing some really advanced stuff. And also what's also convenient is when you are developing, if you have your custom startup config, you can basically set the environment variable startup dir, and if you set this startup dir to some directory, then this makefile will start VPP in that directory, and it will try to use startup.conf inside that directory. So you can really have like different directories with different configurations, and you can just change the startup dir, and make run will just pick the config from the directory. So no need to do a long command line to specify where to get the config. You also have a macro for GDB, so make debug. So it will basically load the GDB and start with inside the GDB.